New paper to improve diffusion LLMs by a lot. It achieves around 3 times lower perplexity, and it's approaching autoregressive large language models. It's very good. It has lower perplexity with just 128 sampling steps than other methods with 2048 sampling steps and still higher perplexity than this one. So it's crazy good. First, let's remind ourselves how diffusion LLMs work. Let's say you have some tokens, and some of these tokens are masked. So by converting mask to an actual token within this sentence, that's how diffusion LLMs generate tokens, generate text. So the first word is masked, the second token is man, mask, reading. So diffusion LLM will convert these masks into actual tokens to generate text. To generate these missing words in this sentence, we're gonna use Denoising Network. And so this is the way diffusion works. I'm not gonna explain it now, but in detail, but I will explain relevant part. So for this first mask, we get a probability distribution over entire vocabulary of tokens. So what I just said is there is a list of all possible tokens. And this denoising network will generate probability for every token to be next token. So high probability tokens are gonna be likely like good next tokens. And tokens that don't make sense will not be. So let's say this first token gets like this token to have high probability, this token gets this token from the vocabulary, this mask gets this token. And we can sample from this probability distribution. We don't necessarily need to pick the highest probability token. There are many ways of sampling, like you can choose from the top 5, you can choose from any according to their probability. But anyways, let's pick some of these tokens. So the sentence could be quiet man who loved reading. Now, depending on if you are using masked diffusion LLMs or you are using uniform diffusion LLMs, some of these tokens might get masked again. So in uniform diffusion LLMs, some of them get masked again. In this case, it's same tokens that were previously, but it doesn't have to be. So the logic behind this is maybe you want to remask lower probability tokens that are selected because maybe model was not so confident in those tokens, so you want to try to guess them again. And because of the previous unmasking sampling, now you may have more unmasked tokens, more information to pick these better tokens. So you mask them again if they are low probability, so you can pick better tokens. But it's also possible to just unmask token once and never remask it again. So that's just masked discrete diffusion. So we repeat the process. Here we also sample from distribution, but maybe now this lower probability word gets randomly sampled. So loud man who is reading. We can keep this word but remask these two now, and loud man who interrupted reading. So this is how diffusion large language model generates text. Big issue. You see here, the model is generating entire probability distribution, but then it just picks one word. So it forgets all of the distribution here. But this probability distribution itself can give us a lot of information about not only which token is good, which other tokens it considered, and it can give us more information about the context within which this token is being chosen by looking at other tokens that also had high probability of being chosen. So this paper is gonna give us a method to actually remember the probability distribution and not to just discard all of these methods, information I should say, all of this information, because it's valuable information that we can also use again. Like, for example, when generating this loud, maybe model could have and should have a memory that previously it picked word quiet there. And so maybe the word quiet was good based on the context. So to summarize, we don't want to just delete and discard all of the information about probability distribution. We want to keep that in memory for this token, so it can reference its past decisions as well when generating for next time. But memory of this token doesn't just help its own regeneration, remasking and regeneration next time. It actually helps every other token because of the attention mechanism, and I'll explain how. So, this token, let's say this is a mask. We're gonna combine it with its memory, and we will combine every other token with its memory, so even the mask tokens get combined with the memory. And the way we combine two tokens, like let's say we have mask and its memory, or man and its memory, is we just add those two vectors. So we add a vector embedding for man and vector embedding for its memory. If we add them, they're same size. So if we add them, this new vector will have both information about of the current token embedding, current token, and the embedding of the memory. So that's kind of magic in the linear algebra or maths. If you just add two vectors, you also add information they encode into a single vector. And now we got juiced up tokens, each token juiced up with its own previous information about its probability distribution, even the mask tokens. And then when we pay attention, attention is paid because this is diffusion transformer. Between every token pays attention to every token. And so if you want to understand how transformers work, you can watch my video coding Llama 4 from scratch and coding DeepSeek V3 from scratch. But basically, when you pay attention between these tokens, or let's point here. So here we have predicted and mask and all and everything. So when you pay attention, each of this token will take up information from every other token. And because every other token also has information about its own past probability distribution, so now this token will take all of this information extra. So it will be enriched with context around of these tokens. And so every token will be enriched with every other token, every other's history, and its own history. So that's what attention mechanism does. It blends information, it adds information. And this is how we can improve diffusion LLMs. And it doesn't matter if we are remasking some tokens or we just generate them once and never remask them again. We still want to keep memory for that token because it will help other tokens when they are being generated or remasked, knowing that. So this mask will benefit from knowing that this loud could have been quiet and had this probability distribution and stuff. So to summarize the whole process, every token also has memory, which is same vector size as the token embedding itself. And they get combined, and so this memory keeps information about the previous probability distribution, and the token just keeps information about itself, the current token. And when they get combined, that's how you preserve information about previously computed probability distribution, and then that can help with attention mechanism giving more information to the transformer, etc. The result is very good improvement in perplexity. So while other methods of discrete diffusion of tokens have higher perplexity, their method is actually even approaching GPT-2 large. This is the usual perplexity for LLM, autoregressive LLMs, around 30 to 40. I've also experienced this. So they're approaching that perplexity. Join my school to become AI researcher, link below. It's free for now, but it's gonna get paid. So hurry up.